All right, we're rolling. Now the next one is multiple proportions. All right, multiple proportions. This is the other one that some of you were like, didn't really make too much sense. So I wanted to go over it. Only one person saw me for a question on it, so I assume more than, and she does pretty well, so I figured other people may have questions on it. The law of multiple proportions states that when two elements form more than one compound, such as H2O and H2O2. What is H2O2? You need to know that today, along with CH4. Hydrogen peroxide. What is CH4 again? And we got one more that we have to know. This guy, NH3. Ammonia. Ammonium is NH4 plus. Okay. The ratio of masses of the second element that combine with a fixed amount of the first element is always, I'm going to make this capital, always a small whole number ratio. Yes, I make my Y's backwards. Deal with it. I don't know why. My wife makes fun of me, and she was observing me because she's a department chair. Oh, your Y's backwards. Yeah, okay, it's backwards, but I know what a Y is. All right. What is the mass in the above example? Prove the law of multiple proportions. Start with 1 gram of hydrogen. How many grams of oxygen are in here? How many grams? What do you get? Okay, I think you're not, you have to do the math. You gotta do the math. You gotta do a little bit of math. I heard it. All right, 8. How'd you get 8?
Because there's 2 hydrogens, so I thought you do half of, I don't know.
2 hydrogen.
So then I did half of the mass of oxygen, but I don't know why I did that.
Okay, so half the mass of oxygen. All right, anybody else want to give me a little fighting chance on this one? Yes. Yeah, okay, so we have to look at it. It's a 2-to-1 ratio. All right, it's a 2-to-1. So total, if I have 2 of these, I have to have half of this, the mass of half of this. So that means this one would weigh what? This oxygen here would weigh what? I hear you. 16. All right, 16 grams. So if I look at this and I do the law of multiple proportions, I would take my mass of O in H2O2, I guess, and I do my mass of O in H2O, and I divide. I'd have 16 divided by 8, and I get 2. So I have a whole number ratio. 2/1 is 2. Yes?
For the homework, did you want the grams of oxygen in the equation or grams of oxygen in the sample?
We're going with the sample. For the whole, yeah, the one was the sample. Okay, because I do all the homework
So
problems
that's
too.
different than this, right?
What's that?
This grams in the sample would be different.
Yeah, and this is why I did this problem right here, because the examples right here.
Yeah.
This one. Okay, so practice problem. I want to see if you and your neighbor can come up with the ratio forming for the next one. 1 gram of carbon is found to have combined with 0.336 grams of hydrogen in compound A and with 0.252 grams of hydrogen in compound B. Show that these compounds obey the law of multiple proportions. So, figure out how you would do that. Anybody give me a number on the top? A number on the top. What's the mass of hydrogen in compound A? It says it right here. What is the mass of hydrogen in compound A? 0.336. What is it in B? All right, divide. Tell me what you get. All right, I didn't get 1.44. Did I do it wrong? I got 1.33 over 1. All right, so if you take a look, I get 1.33 over 1. Now, if I'm making it into a ratio, what do I have to do to each number to make it a whole number? All right, so at this point, if you get something like this, you multiply by 3. And the big news is, we're not asking you an AP question on law of multiple proportions, but what you need to get is, at the end, I'm going to know that this is going to be 4 over 3. So I do have whole numbers. I have a 4 over 3. Yes?
I'm sorry, can we go over how we get the mass of oxygen in the H2O and the H2O2?
Okay, so on this one, all right, you're assuming that we have, if there's 1 gram, all right, so above example, always start with 1 gram of hydrogen. So I have 1 gram of it. Okay, now, what is, see this, where is my, the ratios, where did I put the percentages? On the 2 pages back, I think. 89% oxygen and 11% hydrogen. All right, it's always 89% and 11%. So if I had 1 gram of that, all right, now you can plug into your percents and pull out to get your 8 grams, all right, from the percentages. That easy? Or you can look at it, you can also look at it and say, I have, this technically would be 1 gram of this. So I have 0.5 and 0.5. There's my 1 gram. And then oxygen would have to make up the other part of it. So it's splitting this in half, and you can divide that by 2. There's like 5 different ways you can get there. Okay? All right. All right? Any questions on that? That was a good question. You guys don't like that multiple proportion stuff. You're fine. All right, next. This is another pink. Another pink. Oh no, I'm not at pink yet. Did I skip a page? Dalton's atomic theory. All right, so Dalton's atomic theory, he was a teacher, chemist, whatever it may be. All matter is composed of atoms. All right, and atoms can neither be created nor destroyed. We know that that has later been disproved. We'll talk about that in a minute. The atoms of a given element are identical in mass. Identical in mass, but different from other elements. And then we have whole number ratios. We don't have like carbon 2.5 and hydrogen 7.3. And atoms are reorganized, not fundamentally changed in chemical reactions. All right, so organized. All right, it was later discovered that mass and energy could be interconverted in nuclear transformations, i.e. the sun makes new elements, hydrogen and helium all the time. All right, and Dalton proposed that atoms of the same kind of element were identical. It was later shown with mass spectrometry, I can't even speak, and the discovery of isotopes. That this was incorrect. Mass spectrometry.
Mass spectroscopy.
No, mass spectrometry. I don't know why I can't speak. Okay? So that moves us into the mole. Alright, the mole is very simple. The mole means the amount of a substance. Alright, amount of a substance. The mole, which is the number of carbon atoms found in exactly 12 grams of carbon, 12, is equal to the number of atoms, particles, formulas, units, molecules, etc., found in 6.022 times 10 to the 23rd. You must use the 2,2. This is what AP expects you to use, so don't get lazy and don't use the last 2. You have to use that 2. Alright? So 1 mole of sodium atoms equals 6.022 atoms. Oops. Times 10 to the 23rd, Mr. Times 10 to the 23rd. Atoms Na. Okay? What about 1 mole of water, H2O? Now it has more than one atom there. It has 3 total atoms. How many molecules would we have? It doesn't change. 6.022 times 10 to the 23rd. I just changed the name. Molecules. H2O. Molecules H2O. It does not change. Okay? So now I ask you to create a couple conversion factors for the above. Alright? So that's very simple. All you need to do is if you have an equal sign, alright? That's very simple. So here we go. 1 mole Na over 6.022 times 10 to the 23rd atoms Na. Or what else? Or what? Flip it. Over 1 mole Na. Alright, I could do one for water. Alright, here's water. Let me make it blue. 6.0022 times 10 to the 23rd. Molex H2O. I'm totally butchering that. Over 1 mole H2O. Alright? Let me ask you this. What about moles of H over mole of H2O? What numbers would I put there? Oh. Kind of like when I was doing 12 times 13 with my kid last night. Kind of looked at me the same way. Sorry, can't hardly that. What's that? 2 moles of hydrogen. 1 mole of water. I have 2 of these in 1 of these. What about mole oxygen in mole waters? What would I do? What? 1 over 1. Alright, that'll come in handy later today. Alright, so we have to do this little problem here. I'll do this one, you do the practice one. Here we go. Let's do this together. So I'm going to write this very simply put. Mole sodium, and I want to find out how many atoms are in that. Okay. Take one of my conversion factors. I'm going to do this. 6.022 times 10 to the 23rd. Atoms Na. Look at that. I love writing those out. And I get, if I did my math correct, all right, so see if you can do the other one with your neighbor. Check with your neighbor when you are done. I'm sorry, don't do it with them. Check it when you are done. What'd you get, Ashley? Perfect. Times 10 to the 23rd molecules CO2. All right? Easy? Hopefully that's easy. Let's move on to atomic weight and molar mass. I'll leave that up there for a second. Did you get my answer? What did you get? Okay, I'm rolling. All right, here we go. Don't worry, folks. When I think it's something that's challenging, I definitely slow down. So, you know. All right, next. Atomic weight is the average weight of what? I've gone over it already. Pick your kind of atom in AMU. It is the weighted, I don't know why, I definitely messed this up. Weighted average of the naturally occurring isotopes. Sorry, it's a little bit off. It's one sentence. I pushed return, I don't know why. And we come up to a pink. A pink means super, super, super important. Pink. Molar mass. Mass of 1 mole of atoms of an element, compound, formula unit, etc. Its units are grams per mole. Or grams per mole, because this mole would mean it's on the bottom of the fraction. So you can see them listed this way or this way. This is how AP lists it. Alright? So when the unit's on the bottom, it gives you a -1. It is used to convert mass, a quantity that can be measured in a laboratory, to moles. Fundamental basic point to understand that molar mass unit is grams per mole. So if you calculate moles in a problem and you were given grams, you divide by grams per mole to get molar mass. For some reason, it's hard for people to say that. And I know the first 5 or 6 times that we do a problem later on this year where it's asking you to find molar mass and the gram is giving you the problem, but then you find the moles of something else, you'll have no idea how to put it back together. Just remember, it's grams per mole all the time. That will make your life very easy in this class. AP asks for molar mass on so many things that if you don't do it, kind of makes the class kind of challenging. All right, so if we have this one, find the mass in grams of 1.0 times 10 to the 13th sodium atoms. All right, here we go. Start with what I'm given. And now I have to look on my periodic table. All right, so I'm going to have 1 mole Na. I have to get rid of it. And I have to then multiply it by its mass. What is the mass of sodium, folks? On your periodic table. All right, somebody see if they can give me an answer for that. Practice your calculators. Now's the time. If I'm doing exponents and I don't use parentheses, put my numerator in parentheses, divide parentheses for the denominator, you will not get it correct. You will not get it correct. Okay? 15. What'd you get? Oh, yeah, sorry. I looks like pulling teeth. Making you problems. I want you to be successful. Well, what is it? Did you guys agree? 1 point something? I didn't get no 1 point something, nothing. You gotta use parentheses. Look it, you're multiplying, let me highlight.
3.81.
Multiply this, by this, by this. Divide by that. Multiply together. Yellow divided by green. Use parentheses. This is exactly why I said to do this. 3.8 times 10 to the negative 10th grams of sodium. It's not, there's no other decimal point because this only has 2. Can't have more than 2 on your answer. Alright, next. What is the mass in grams of 0.15? Alright, what would I do for my next part here? What would I do? Fernando.
You multiply by 6.022.
I only need the mass. I don't need atoms. I don't need anything else.
Oh, then you multiply by the mass.
Which is?
4.
There you go. 4.00 gram helium. That's a 0. And that's all you need to do. 0.60 grams helium. Glad we did this problem because you might think you needed to use Avogadro's number. All right. Real quick, you're going to practice your molar massing. Should not take it long. I went over it last class. So do your molar masses, check with your neighbor.